La verdad es que es un placer. I'm so sorry because I will speak in Spanish. Es un placer presentar a Sane Stepka. Ella es letona, de Letonia, pero está trabajando en el Weizmann Institute for Science de Israel, después de haber pasado, bueno, es arqueóloga, después de haber pasado por varios países, incluida su máster y etcétera, su carrera en Edimburgo. Parece ser que en Letonia hay pocos arqueólogos, no está muy desarrollada la arqueología, digamos, está desarrollada, pero hay muy pocos arqueólogos, y ella se empeña en que quería ser arqueóloga, y se fue a estudiar, ya le aconsejaron que se fuera a estudiar fuera, y se fue a estudiar fuera, se fue a estudiar a Edimburgo, y allí estudió la carrera, estuvo haciendo las prácticas de excavación, porque claro, es muy buen sentido el suyo, porque veréis que, en lo que trabaja no es muy de campo, digamos, pero ya desde el principio se empeñó en que tenía que excavar, porque tenía que saber cómo salían los restos, cómo salían las cosas y cómo se podían manejar y gestionar estos restos arqueológicos. Total, que ahora mismo está haciendo su tesis doctoral con Felipe Natalio en una cosa muy interesante, y es lo que nos va a contar, que son señales ocultas de presencia del fuego en los siles de los yacimientos. Es decir, cuando tenemos yacimientos, ocupaciones humanas, en las que no hay restos de sedimento alterado térmicamente, no hay restos de que los siles hayan estado quemados, pueden detectar a través de unos métodos que nos explicarán si realmente han estado quemados o no han estado quemados, si ha habido presencia de fuego o no ha habido presencia de fuego. Con este desarrollo y con este punto de vista, publicaron hace relativamente poco un artículo que todos vosotros conoceréis, que es el de las huellas de hogares en el yacimiento de Bron, lo cual es importantísimo porque efectivamente hasta la fecha no se había detectado ningún tipo de alteración térmica. Bueno, pues sin más, la dejo paso a ella para que nos explique lo que está haciendo, porque nos hemos sumado a esa colaboración en el proyecto de Atapuerca para tratar de ver en algunos niveles, por ejemplo, en T10-2, que es el gran impacto del Bison Berg de Dolina, si pudiera haber habido algún tipo de hogar o lo que sea que no haya quedado reflejado. Entonces empezamos la colaboración y ella nos va a explicar sus métodos. Thank you very much for coming here and to stay with us and to talk, give this talk with my wonderful work for us. Thank you.
Thank you. Thank you for the introduction. So I've been introduced. I'm happy to be here. You got a long introduction, so all I'll say is today's talk, so I want to do kind of two parts. First, to talk about the work we've done already, and then the work about collaboration, where we are at, what's happening, what we are doing, okay? Two things. Because of my background, I will use the words flint and chert as synonyms. Sorry, I know this is an issue for people, okay? Second thing, I come from Latvia, we come from different parts of the world. I live in Scotland. When I get excited, I can talk fast. It might be difficult to understand, okay? If that's the case, wave also for people on the Zoom, hola, by the way. Okay, let's begin. So, work in the past first. When we look at the earliest evidence of fire, there are only a few archaeological sites in the world that are older than 500,000 years old, and we have burnt archaeological material. So we have Watkins Caves in Africa. We have open earth sites, Kobe Forest, Somalia in Kenya, as well as Gesher Benot Yaakov in Israel. And we have a rock shelter not far from here, Hueva Negra. And I want to introduce today to you a new site that we can add to the list, and the site is called Evron Quarry. Evron Quarry is an open air site. It's located in the northern part of Israel. The site was excavated in the 1970s and 80s by Professor Ronen. You can see the excavation plan here. Each of the red squares is 5 by 5 meters, so you can appreciate the size. The archaeological level was found around 8 meters from the surface, and is dated to more than 800,000 years ago, based on evidence for reversal of the magnetic poles in the layers above archaeology. Okay. And the site was excavated in the 1970s and 80s as a rescue excavation. So it no longer exists today. They make a landfill there. Okay, so we cannot go back to the site. What was found in Emerald Quarry? First, we have chert or lithic artifacts composed of chert or flint, of course. So we have flakes, including retouch flakes. We have pointed tools and notches, cores, and other types as well. It's Michael Chazan who studied the assemblage. Next, we have faunal remains. We have a hippopotamus species. We have 2 species of elephant-like animals, I will say, for the lack of my Latin. We have aurochs, gazelle, and other species as well. And finally, attached to some of the bones, we have sediments as well. Okay, so this is the material we have from Evron Quarry. And the way our project came about was that Felipe Natalio, my supervisor, he was looking for an old site where to continue the lab's research on fire. Okay, and Leora Kolska-Horwitz, she's a zooarchaeologist, and she had access to the Evron material. And she said, okay, she brought a few samples to our lab of the bones, faunal material. And she told us, but listen, there was no signs of burning during the excavation. We have done the research on the bones. There was nothing found. Basically, there are no expectations, and keep your hopes low. And as Felipe says, we should have made a bet at the time because this turned out into the work I'm presenting to you. Okay, so our research question is straightforward. Is there evidence of fire in the material from Evron Quarry? We started off by looking at the bones. We used a well-established method that involves Fourier transform infrared spectroscopy. And here what you see are 2 FTIR spectra of bones. And the indication for heating we used in this particular study was this small peak here at 630 wave numbers. This peak occurs during hydroxylation of bone mineral, which is something that happens at high temperatures. Okay. So from Evron Quarry, we looked at 87 pieces, fragments of bones altogether. These are here to the different excavation squares that were found in. And we found that 14 of them are burnt. You can see the data here. This is only the relevant section of the spectra. So you see the 630 peak in the upper first 14 spectra. And here we don't have it. So there are some samples also that were not burnt we're showing. Okay. Now there's a but here. We know that 7 of these burnt pieces, they all come from one individual specimen. They come from a large like tusk, like elephant tusk. Okay, you can see some fragments here. The other of these burnt part pieces here, we looked at them and we can tell that they come either from tusk or from teeth based on the morphology of them. So it is possible that we actually altogether have one burnt specimen, that all these belong to one. Or it can be that we have multiple. We cannot know for sure, but whether we have one burnt faunal remain or more, the truth is that we do have burnt faunal remains from Evron Quarry. Now, next we looked at the sediments. And what we found is, I will not show the data, we also used another well-established FTIR method, and we found that no sediments are burnt, exposed to high temperatures, including the sediments that are attached to the burnt pieces of the tusk. So the tusk is burnt, the sediments are not burnt. How can this be? I see 3 scenarios. First is it can be that the tusk was burnt in a place and then transported even a little bit after the fire. Second can be that the sediments that we found next to the tusk now were actually deposited later on. Okay. And the third can be that both the tusk and the sediments are in situ, but maybe the sediments were, let's say, at the bottom of the fire on the ground, so they didn't reach high enough temperature to leave the FTIR signal we're looking for. Okay. Next, we looked at the lithics. So for the lithics, we used the recently established new method in Felipe Natalio's lab. So, and I want to introduce you this method first, because it's also something we will use in active working. Okay. So the method is based on Raman spectroscopy. This is another type of spectroscopy similar to FTIR, but it gives us more information on the different components of the flint chert. And the second part of the method employs artificial intelligence. So how do you go about establishing a new thermometer, if you want, for heated flint? What Aviad Agam, Idouazuri, and colleagues did was that they took flint nodules from 10 different flint sources in Israel. Then they broke these nodules in pieces and heated the pieces to different temperatures in the oven. And they measured these pieces with the Raman spectroscopy. And they got spectra as a result. Now, when we looked at the bones, we saw we were looking for the presence and absence of one particular peak as an indication of fire, right? In the case of the lithics, it's more complicated. Let's have a look. What you see here, this is an average spectrum of many pieces of flint burned to different temperatures, okay? The peaks represent the main components of flint. So we have the quartz and mogonite crystals, as well as the D and G bands belonging to the more organic part, the organic part of the flint. And what we found is that most of these peaks show changes depending on the burning temperature, but the changes are not linear to the temperature. What do I mean by not linear? Let's have a closer look at this mogonite peak. Yes, where it's red and purple, those are the areas that change the most. Okay, let's look at the mogonite peak. Temperature on the x-axis, the intensity or the height of the peak on the y-axis. You can see that overall, with heating, the peak becomes smaller, but this change is not linear, you see? And this is the case also for the other areas affected, but not exactly the same. This is where the complexity here comes in. What we have on top of this is that flint chert, it's a heterogeneous material. Okay, it can have slightly different composition, especially when the nodules come from different geological sources. On top of that, when you measure the flint in one particular location, again, because it's heterogeneous, when you do a measurement nearby, you can get a slightly different data. So in fact, it's not enough to do one measurement. For this study, we did 27 measurements. Okay, so quick math. We're back here. 27 measurements per one piece of flint. We have 10 different sources in Israel times multiple temperatures to which we heated. We end up literally with thousands of data. So what we need to do now, we need to look through all these data, look at the changes that happen in these spectra, and correlate these changes, nonlinear changes, to the temperature. Okay. Good luck to a PhD student. It's difficult for a human to do. They tried some analytical, approved methods that didn't work out. So difficult for human. This is a perfectly fine data set for artificial intelligence. This is why it comes in. Okay. So Ido Azuri, many data. Ido Azuri from the Weizmann Institute, he built a deep learning model and trained it on this data set. And what came out was that this model was indeed able to learn and correctly predict the temperatures. What does it mean to train a deep learning model? Basically, we show the deep learning model a spectrum, and we say this flint was heated to 400 degrees. This flint was heated to 600 degrees, and so on and so forth. After that, the model learns. After that, you show it some data it has never seen before, and you ask, to what temperature was this heated? Okay, and we know the temperature. And turned out that the model was indeed able to do so, predict the temperature with an error of 103 degrees on average. Okay, so now we have our thermometer, and we can apply it. We can take a lithic assemblage, in this case from the Hebron quarry. Furthermore, it will be from Atapuerca. Okay, we do the Raman measurements. We feed them through the pre-trained deep learning model, and we get our temperature estimations. Okay, that's the method. So what we did in Hebron was that we, or rather Professor Michael Chazan, chose 26 lithics that represent the assemblage, and we measured them. What we found out: 26 lithics on the x-axis, estimate the temperature on the y-axis. The three different colors represent the three different excavation squares the lithics come from. We only checked 3 squares, okay, 5 by 5 meters. So first, what we see, there are some lithics that have been burned to really high temperatures. And then we see this gradual mix of different temperatures. What we also see is that the colors are, all 3 colors are on top, all 3 colors are on the bottom. So that means in each square, we have some lithics heated to high temperatures and some heated to low temperatures. Okay, so we had burnt faunal remains. Now we have burnt lithics as well in Hebron quarry. The question, of course, was it a hominin fire in any way, shape, or form used, or was it a wildfire? What can we do? First, of course, let's look at the distribution. The 3 squares where the lithics come from are these 3 here. Okay. The burnt faunal remains, most of them come from L5. One particular piece comes from L4. So you see that the burnt material comes from quite a wide area. Okay, we don't have one particular square where something is there, and then we can maybe imply, and then it will require loads of more work to say that this was a bonfire or something. Okay, this is not the case. Another thing we can do, we can look at the depth of the burnt remains. So these 2 are the 2 squares here where we found most of the lithics, and the bubbles are the lithics that we measured. The larger the bubble, the higher the temperature. You see that in these 2 clusters, we have flints burned to high temperatures and low temperatures next to each other. The idea is that if it was a wildfire, and if it's the best case scenario, it could happen that a wildfire goes across a flat area. We don't know if it was flat to begin with, as how much, okay? Best case scenario, it could predict similar temperatures throughout. This is not the case in Emerald Quarry. However, as I said, the site was excavated decades ago. We cannot go back to the site. We cannot bring this material forward. So at least personally, I think that in Emerald Quarry, we cannot distinguish between common fire or wildfire, natural fire. Okay, but it is true that in Emerald Quarry, we have evidence of archaeological material around 1 million years old, which is burnt. So we can add Emerald Quarry to this list of sites. Okay. On a personal note, I want to say that I used to work in commercial archaeology, and we used to box away thousands of artifacts and put them in boxes, probably never or sometime to be looked at. So for me, it was personally nice to be part of this project where we unboxed decades-old cardboard boxes and learned something new about the lithics. And the hope is that if we apply this method that only requires the flint artifacts and nothing else to all the archaeological sites of early sites, perhaps we can add more data points to the to test the hypothesis that maybe it was the use of fire and cooked food that started that advanced the evolution of our large brains already millions of years ago. Now, time machine. Fast forward to Kesem Cave, which is a site around 300,000 years old. The relevant layer I want to talk about. Why Kesem Cave? When in Kesem Cave we have evidence of fire. They have evidence of fire. So they have basically a bonfire. They have evidence of an ash layer, quite thick. Then there's a gap, no ash, and then there's another evidence of ash layers worked by Strakagross. So we know that there was a use of fire in this cave, probably quite intense over a long period of time. When Filipa with colleagues developed the lithic heating method first, they were looking for old archaeological sites where to test the method. Okay, so the idea here was we know that there is fire in this cave. Let's see if the lithic method works as well, i.e. can it identify archaeological burnt lithics rather than just experimentally burnt in the lab. Okay, so this is why they went to this site to begin with. And they started first, they chose lithics that have potholes, so visual signs of burning. Okay, and they found indeed, this is the estimated temperature, that these lithics that have potholes have been heated to high temperatures. Okay, great. The method works in an archaeological site. Great. What they then thought was that they did another experiment. They took two types of lithics coming from two mapping sequences. They had blades, flakes, and they had blades. And they measured the temperatures of these lithics as well. And what they found that both of them had been heated, and flakes were on average heated to higher temperatures. Now, they took few lithics out of a layer of thousands, okay, more than 20,000. So we stopped the interpretation. I stopped the interpretation there. However, here, what I want to put forward is the point, the idea. The idea is that in early archaeological sites, and later we look presence, absence, fire. In early archaeological sites where we know it's quite sophisticated mapping technology, so there is a theory, idea for some people, truth for some not, that perhaps our ancestors in the past used to heat the nodules before they napped the flint in order to improve the nappability. So if that was the case, who did it, when, where? Was it for particular production sequences or for everything? Was it the whole nodule heated, or maybe part in the middle of the sequence, some part of it was heated, and so on and so forth? Another type, let's say that there are experimental studies that show today that this particular chert, when we heat it and then we nap, we can nap it better. Great, let's test it. Maybe the ancestors also heated it before, but maybe not. Okay, so both ways, but this is methods opening the doors to study also that fire technology going together with flint method. Now, this is work we did in the past. Fast forward again, Atapuerca. So this is why I'm here. Very shortly, I'm not here to introduce to you Atapuerca, it's the other way around, okay? But very rich in archaeological sites and in artifacts, less rich in the evidence of fire. So this is why I'm happy for Professor Marina Martinez, who made the collaboration together with my supervisor in Israel, Filipa Natalia, that we are now going on a hunting expedition, hunting for fire in Atapuerca. And thanks to some of the people from IPFES already, we have some preliminary results and work, and I will show you what we have been doing. So in Atapuerca, again, straightforward research question: is there evidence of fire? We are going to begin the work in the famous bison bed. Again, I'm not to introduce it to you, of course, but the reason we go to the bison bed is because we have a good evidence there for activities of butchering and napping in situ at the site in very rather thin consolidated archaeological layer. and the site dates to around 400,000 years ago, when the use of fire becomes more prominent. Okay. And so this is part of why I'm here today and yesterday. That yesterday we selected some of the lithics from the Weizenberg layer, and in particular we're focusing to this area here, which is deeper in the cave and just flat. Okay, so let's see what we get from there. Now, before we can measure the lithics, as you learned before, what do we need to do? We need to build a thermometer. Previous work was done in Israel on Israeli flints. Okay, now we are moving to a new region. So we start with a reference collection. Now, the method itself, so it almost literally is composed of experimentally heated reference collections. Okay, so no reference collections on sources around the sites, no method. This is why it's very important that we're building our work on top of the work that was done by Dr. Maria Soto. Without this, it wouldn't happen. Okay, so Maria Soto identified a number of sources of lithics around Atapuerca. A few of the sources are here, and she identified 3 varieties of chert of Neogene period and 2 of Cretaceous period. So in terms of the geological timeline, us today, beginning of Earth, let's say. So Cretaceous. This is also all that lithics we worked before in Israel come from Cretaceous. And now Neogene, the separation between Cretaceous and Neogene is around 40 million years or a little bit more. So we are expanding the method for Neogene, which is a new challenge for us, and also making it particular for Atapuerca. And so around 3 months ago, thanks to Maria and Marina, they sent us to Israel 5 nodules of Neogene flint, and we started the work on them. So what I did to begin with, I broke these nodules in small pieces, and I heated these pieces in the oven. So you can see, for example, here, before and after heating to 700 degrees, you see the color change. So we do this to the different temperatures, each of the 5 nodules. This is our reference data that we are working on. Okay. Next, we measure the data with Raman. Remember before I told you we took 27 measurements for one lithic, okay? So these here are 27 measurements of a piece of nodule number 1, which was not heated at room temperature, RT, okay? So just so you see how it looks like. Next, the same piece from the same nodule heated to 200 degrees and 700 degrees. Do you see differences? Yeah, you see, but what's the main one? The slope, okay? Now, this slope, it derives mostly from fluorescence, and that comes from the organic matter, as well as defects in the crystal structure. So it's informative, but it's a small part of the components of flint. So actually, we'll pay to it some attention, but not all. We get rid of the slope, we baseline the data. And in order for us to be able to see more visually what's happening, I baseline and I average. So this one spectrum is the average of these 27, okay? So room temperature average, 200, 700 degrees. And then we see, wow, they look more similar, right? Not as easy to compare anymore. Let's overlay them one on top of the other. So now you can see, okay, there are some differences. Room temperature not heated, and the heated samples, these peaks go down. These are the peaks representing the organic matter. Makes sense, we burn them away. Some other changes here. So I see differences with I. We fed through a deep learning model. It was already started to train it on this data as well from all the nodules, and it works. The module is learning. Why am I just saying you? It works, and that's it. I'm showing you nothing, okay? So trust me. The reason I tell you this is that in order to get some kind of quantification how good the deep learning model works, you really need a lot of data and you need to do loads and loads of experiments. As I said, some samples the model is learning from. Some we use for testing. We need to make sure match these samples all the time to make sure that what we get is really solid. So this validation experiment will happen at the end. At the moment, we are just getting the sense that, okay, it works. Okay, this is where we are. So it works, great. Let's heat them more and let's develop our database. This is what we were doing, and we came across something. Look at this here. A piece of this nodule heated to 400 degrees, and I separated here some of the spectrum. You see, they're kind of 2 groups. They're not the same. You see this mogonite peak, larger peak in those samples here, less here. It's also a bit noisier here. What's going on is the same sample. Then we look, this is an image, microscope image of where these particular measurements were taken. 50 microns, so less than a millimeter, everything, all the dots here. And what I found was that all these measurements come from one particular area here. A bit difficult on the screen, but you see here, this area is more edgy, like larger crystals, and this is kind of smoother, so maybe smaller particles. We went back to look at the surface of the chert. This is a scanning electron microscope image of the same chert. And what we see here, also you see these edgy, larger crystals, a fine area here. So this is, I think, what I see. We know from the work of Maria Soto, the Neogen chert, the way it's formed was that the silica, the mineral forming the chert, misplaced previous crystals that were there before gypsum. So I think this is what we see. These were probably before gypsum and now are silica. This is a new or later silica. Anyway, you see two phases. Okay, in this case, we were lucky. In this particular measurement, the spot area was positioned so that we got like, both of them. But sometimes you maybe measure only here. Sometimes you maybe measure only here. So the method cannot work, okay? We cannot have two different materials of the same piece heated to different samples. How is the model able to differentiate between temperatures if this one nodule consists of two different parts, okay? So what we did, we said, this is no good. We established a new method for acquiring the data for Atapuerca cherts. So this is how the method looks right now. This is the method that was before. The images are scaled. So now we are literally looking at much more larger area. It's 0.5 millimeter by 0.5 millimeter. And we are taking measurements of larger areas. And it takes 36 measurements as opposite to the 27 before. Okay, new method. Good. What do we do? Remeasure everything. Okay. Oh, before we remeasure everything, Dr. Mariela Pavlan, she's in charge of the Raman microscope that we are using for the study. And for the last 3 months, we have been back and forth with her all the time and improving. So a lot of this is also thanks to her. Also, her instrument, it's a bit more accurate than the instrument we were using before for our particular needs. So there are some samples we measured in both, and we see that we get more reliable results from Mariel's instrument. So it's good for Atapuerca, okay? So thanks to her. New method, let's remeasure. Okay, these are small because I don't want you to look at the details. In general, 3 nodules heated to 2 temperatures. Look at what stands out. Every now and then, there are some outliers, you see? This is normal. Flint is heterogeneous. Sometimes you hit another small piece of another mineral. This is my job to take these out. But look here. There are many spectra, many measurements that have this extra peak here and this extra peak here. You see? I checked. This peak lies to calcite and calcium carbonate. It's fine to have small particles of this in general in the environment. In this particular nodule, there's more of them than in the other 4. We looked at elemental analysis as well. So again, scanning electron image, and the different colors just show different elements, and calcium, part of the calcite, is in yellow. So you see really in this nodule, there are some areas where we have particular particles containing calcium, so probably calcite, which we see in Raman. Now, another issue, a new method. What now? Well, no, wait a second. That's why I came here and we took some more samples, including the archaeological samples. And what we will do, we'll measure first the archaeological samples, see if they are rich in the calcite or not. Do we need to tackle this problem or not? If we need to, we'll just take more measurements, more controls if we need to. We know that the measuring method at the moment works, leave it, okay? Now, you're very patient with me. Remember that many slides ago, I told you we did some initial tests with the previous method and it worked, okay? Remember that? And now I'm showing you some really details all the time saying we improved. Why are we improving? I told you before, the method learned, it works. Why do we need to improve anything? Well, how good is the thermometer? I told you before, for everyone, we got the error of 103 degrees. Where's that? I'll show you. Work of Pedro Azori, who is the deep learning person here. This is what we got the validation experiment for Evrel and for Israeli sites, okay? After all the dealing with reference samples. So what we have, nodules from 10 different sources, okay? Pieces of the nodules heated to certain temperatures, and the estimation of the deep learning model. So for example, all these pieces, like around 250 measurements that were come from cherts heated to 800 degrees, it's also predicted around 800 degrees, right? But you see for different temperatures, there's different standard deviation error, okay? The average of this is 103 degrees, as I said before. So first, because the nitrogen chart turned out to be a bit more complicated, we know that if we don't handle the methodology how we sample, these errors are going to go all over the place most likely. Okay, we want to get as good as possible. Second, you see before here, these two are kind of overlapping. Okay, the median is here, most of the points are here, most of the points are on top, but still, this is between a room temperature, so not heated, and heated to almost 300 degrees. Why can this be? So this can be because the actual nodules in the field, they have some thermal history. In Israel, it's hot. I can easily see that in the desert, they could have been heated to 50, 60 degrees. Something else could have happened to them in the past. This error in then comes from all of our error as well. All the measurements are heating, the Raman instrument, the optics, and so on and so forth. And it also comes, I think, most likely, personally, I think, from the organic matter in the flint. Because as we start to heat the flint, that's the first one that gets affected. It goes away, okay? And the organic matter from different sources, it just can be different to begin with, different contaminants. So it probably is going to be, might be the same case for that samples around Attenborough as well. And this is why we're trying to work so hard to improve the method to get all these error bars as small as possible, so our thermometer is as accurate as possible. Okay. Now, one part is that all the data we put in. The second part, of course, is the model itself. I won't go through details, don't worry. This is the deep learning model. Basically, here we have our spectrum going in. What is our spectrum? It's just numbers, okay? X-axis with some numbers, Y-axis with some numbers. That's all it is. And it goes through the deep learning model. In the end, we get one number, which is the estimated temperature. Everything in the middle, they're now data scientists. In the end, in the day, someone who doesn't tell me this is wrong. And then they all in the middle are two mathematical actions, plus 2 plus 2, and multiplication 2 times 2. Okay, but they happen literally millions of times. This is why we are drawing maps to see what happens when and so on and so forth. Okay, now we are this time here, as I said, we have improved our method, so we will be giving in to all this new type of input. So we'll also adjust this a little bit. And Ido Azuri has this already adjusted, and he's working. We are measuring samples, and once I give him the full data set, it'll be up and running, and he will tweak a little bit as needed for the Attenborough. If he can improve it a little bit, we will see what happens. So this is ready. Next, another reason why we are trying to get the error bars down to get that method as accurate as possible is because we want to challenge the deep learning model. We want to ask not only what temperature will the liquid heated for, but also for how long. Why do I care about this? As I said, in the case of Hebron, for example, and many open air sites, we cannot distinguish whether it was a wildfire or a hominin fire in any way. Okay? So here is an idea, a hypothesis we have. If it is a wildfire, it usually spreads across area with quite a speed. Even if there's a large piece of wood that really burns all the time, it will take only some hours for the wood to burn out. But what happens in a bonfire, where hominins or hamsters can sit, we can feed it fire, so we can have it burning for hours and hours and hours if we want to. Okay? So the idea here is if we can extract information how long the liquid was heated for, then perhaps if we find the liquid that was heated for 10 hours, it's more likely, maybe, that it was a hominin fire than a wildfire. Possible. More indication so far. I'm giving you the idea. Okay. How do we want to do this? It will be challenging. We understand. Probably the difference will not be huge. So how are we going to do this? We'll start with a very simple experiment. We'll take some liquids, we'll heat them to 700 degrees all, but some of them for 2 hours, some of them for 7 hours. Train the model and ask the model a very simple question: 2 hours or 7 hours? No other choices. 1 or 2. Okay. So we measured some samples for this experiment, and just very briefly to show you 2 hours, 7 hours, to see how similar they are. Okay? And we fed this to a deep learning model, and what happened? The deep learning model, again, I cannot give you data because it's not works. The deep learning model learned. It was able to distinguish between 2 and 7 hours, but not good enough. What do I mean? Like not well. If it was random, when we test it and show it 2 hours, 7 hours, and ask it for result, if it was random, it would be 50-50, right? 2, 7, 2, 7, random. We are getting more than 50%, but one time it can be 60, one time 75, and there's not enough data. So Ido Azuri, he says he's not sure enough. The model is learning, so this is good. When it's really not learning, it's 50-50. It's learning, but it's not sure that what it's learning is actually the temperature. What do I mean? If you show images to a model and you want us to distinguish between cars and buses, maybe it will do it with some accuracy, but maybe it's because there are more buses in red color. It's looking at something else on the time. Make sense? Okay. So we are thinking, okay, this is a really challenging one. Looks like you need loads of data for this one. What to do? So then I thought, okay, wait a second. Let me have a look at what I see. And I looked closer to the differences between these two data sets, and I saw that for 4 out of 5 modules, there are changes that are consistent. One is that this speed, GT, becomes smaller, which represents the organic matter more. Another one is if you zoom in, there's another peak, which consistently for 4 out of 5 modules with longer heating becomes smaller. By the way, the 5th module is the one that's rich in calcite. I didn't know at the time, but now I know. So it might be, there is some pattern. Again, I don't know if this is the bus and car, so 2 hours, 7 hours, or this is the red color. I'm not sure. But the fact that the organic goes down with longer temperature, this makes sense to me. Okay. So we're thinking, okay, maybe it's going to be challenging, but maybe more than it's more. So add more data. Adding more data, what do? Heat another 100 modules with the same temperatures, fine. But what else? What is a heating experiment? What does it mean to heat something for 2 hours? And this is something we had an earlier meeting with Marina, and she gave us really good tips about this. So this is your heating experiment. Temperature of the oven, 700 degrees. We cook, and the 2 hours or 3 hours here for which the lithic is in the oven. But the oven to begin with, it heats up, okay? And then it cools down slowly. So actually it's 4 factors. The temperature, the duration, how fast does it heat up to 700 degrees in 1 minute, which could be a heat shock for the lithic, and that could give us way more data than the actual duration, or does it take hours for the heat up? So eventually we want to distinguish between 3 and 7 hours, but we need to look at other factors as well. So one is the heating rate, and I have prepared some samples that are giving us heat shock. One is the heating duration, 2 7 hours. This is just arbitrary. Maybe we need to heat for 100 hours to see the difference. So we'll heat some samples for longer as well, and we'll look at different temperatures. All these samples I have ready, but we put them to sleep, rest a little bit. Why? Because this is a high risk, high work exercise, okay? You can do all this and come up with nothing, or we can do something maybe in the jack, but we don't know. So first, we're going to have the thermometer that we know that for atmospheric lithics, we can go and look whether they've been heated or not. This is the main thing. We want to look at the archaeology, and we want to get some answers about the archaeology. Then let this sleep a little bit, we come back. So in total current status, the method which estimates temperature for Atapuerca is on its way. We have improved the method acquisition, okay, particularly for Atapuerca. And current status, good. Looks like the model works. With the previous one already, we have improved it. So now we are gathering more data. Next, we will train the model once the whole data set is there and there's loads to train it. And then we go to Grandolina lithics, which I'm bringing back to Israel in a few days. The temperature and time estimation model, as I said before, might work, future work. So this is where we stand in a moment. And this is where I tell you, thank you very much. And on a kind of, thank you very much. On a personal note, I would say that, as Marina said, I come from Latvia. We have like 40 archaeologists in the whole country, okay? So people don't talk about archaeology. No one talks about archaeology. No one does archaeology. But here, the 2 days I'm here, you have a whole space here with so many people doing archaeology, and it's really inspirational. Will we find or not find evidence of fire? I don't know. It's not up to me. It's either there or not. But I will try to do my best to get solid results, whatever they are. And so, yes, thank you for the new colleagues. It's nice to cooperate. Thank you to the people I had the pleasure to work with for the Hebron, and my friends and members of Philippus Lab. Thank you very much.